Okay, so today we are heading towards compactness. We will definitely get there. But before we do, I just thought it might be nice to do a couple of things as an exercise. So we have this theorem where you have, was talking about the sort of interaction of unions, intersections, open and closed. Right, and it said it had four parts to it. One, that if you have a bunch of open sets, then the union, even if it's infinite, the infinite union is still going to be open. Two, if you have a bunch of closed sets, then the infinite intersection is still going to be closed. Right, and then there were corresponding statements for finite sets, right? Like a finite intersection, EI to EN is still open. A finite union of closed sets, finite union of closed sets is still closed. Yeah. So. Let's think about these first two first. Can anybody give me an example of an infinite collection of open sets whose intersection? So, one, find a counterexample to the claim that. If you have a bunch of open sets, then their intersection is still open. Okay, that's false. Okay, can somebody think of an example, or take a minute and try to think of an example where you've got an infinite number of open sets and their intersection is not open anymore. Or similarly, you have an infinite number of closed sets, and their union is no longer closed. Okay, talk with a neighbor for a little bit. Talk with somebody nearby. Okay, anybody want to throw something up? Anybody want to suggest give an answer? Rishi, go ahead.
One example you could use for an infinite collection of open sets whose intersection is not open is in the real line, if you take the set of open intervals from -1 over n to 1 over n for all natural n, then you're like open intervals. Yeah, so then all of those sets are open, but if you intersect them all, then you just get the singleton 0, which is not open. And then for closed sets, you could just use the complements of all those.
Yes, that's true. Okay, so yeah, so you could say, take here's 0, and you take, -1 to 1, -1/2 to a half, -1/3 to a third, et cetera, those are all open sets, right? But when you intersect them all, what's left? Well, only the origin is left, right? Just that dot there, right? Is that an open set? No, right? Because you can't, because every point would have to be interior. This point would have to be interior, but there's no open set that's right. If the set consists of this single point, well, you can't find an open set that is contained. You can't find an open interval around that point that's contained in here, right? Okay. Yeah. For the second one, does anybody have another example for the second one? Like you have a bunch of closed sets and the union is not closed. Here's a simple one. You could say like f of n. You could take say like f of n is say -n. Right, this interval, that's a closed interval. The union is going to be the entire line. Well, that is close, actually. That is close, sorry. That's a bad example. Okay, we'll use Rishi's, we'll take the complement of all those guys. So let f sub n be -1, 1/n complement. Yeah.
I think a simpler one you could use is just close, or like half open intervals from -infinity up to closed at -1/n. I think that might work. Or just going from 1/n off to infinity.
Okay. That's pretty similar to this, yeah. to your first example. So let's just stick with the first one. The first example, you take the complements of those guys, -1/n, 1/n, right? So you take things like this, right? These guys are closed sets, right? And then when you take the union of all of them, well, what do you get?
Just the complement is 0.
What do you get?
Sorry.
Harrison?
Complement 0.
Okay, so you end up with just everything but the point 0, right? And that's not closed anymore because 0 is a limit point, right? We end up with this, the whole real line excluding 0, right? But that's not closed because this is a limit point but not included in the set. Okay. Okay. Let's just for practice, see if you can write down a proof for try to prove C. Try to prove C that if you have a bunch of open sets E1 through En, then their intersection actually is open.
How's E n and E alpha?
Alpha is just an index. Here I'm using numbers as indices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm using natural numbers as indices. Here, this alpha might be like over some arbitrary index.
Oh, sure. Okay, so just find an example where the opposite is true. Okay. Sorry,
Yeah. So this was for maybe an infinite set of indices, and then here we've got only a finite set of indices. Yeah. So both of these are false. Both these are false. That's why we were looking for counterexamples. Okay, talk with the neighbor for a minute, just about what your idea is. What's the idea?
Drawing a picture, like this map, this dash line, like this
Basically, what we said, you know, there's not hard, take the converse one, if we forward the converse towards, then A, that should change. And then the distinction between A and B, so it's that A and B are for an infinite number of sets, so there's no like upper bound.
I just essentially want to say that, like,
And then say
one of them is
you're
an
restricted
exterior,
to your,
but the other one has to be
there's a finite number.
so it's no longer a set. It's on the board, so there's also not in the set.
Can we just find two sets that are intersected?
Yeah, but I think you can also have like.
Okay, so, sorry, what I had written up here was probably completely confusing. I wrote the intersection of En, but I had written, you have sets E1 through En, and then I wrote the intersection of En, which was gibberish, right? What I should have written was the intersection of Ek from K equals 1 to N. In other words, the intersection of all these sets is still open. So you have a finite collection of open sets, and you want to show that the intersection of this finite collection of open sets is still open. Okay, right. So we want to show that the finite intersection of these guys is open, right? In other words, that what does open mean? Don't you just tell me what open means? What does open mean? Is it?
That every point must be an interior point.
Right, so i.e. given any x in that thing, we can find a neighborhood around it that's still contained in that set. Right? Every point is interior. Right? We want to find a neighborhood that that's centered at that point and is contained in the intersection, right? So you've got a finite bunch of sets, right? I'm just going to draw 3 of them, right? And we want to find, we choose some point inside the, intersection, and we want to show that we can find a neighborhood around that point that's still in the intersection. Okay? So what's the, Izzy, go ahead. You look like you're impressed.
No.
No. What's the idea? Anybody have an idea? Like, what if I had just one set? What if I just had one set? Let's use 2 sets. What if I had 2 sets, right? We want to find a neighborhood around here that's contained in both of these sets simultaneously, right? So, anybody? We know that each of these guys is open, right? Each of these guys is open. So what does that give us? What does open tell you?
There exists some neighborhood of the point that's completely contained in each set.
Yes, right. So like, let's say the point is here. This guy is in E1. E1 is open. So I know that there's some neighborhood around it that this guy is interior to E1. Right? That's what open means. Right? I also know that E2 is open, and this guy is in E2, so it's interior to E2. Right? So I know that there's some neighborhood contained in E2. Right? How do I find a neighborhood that's contained in both E1 and E2?
Take the minimum R.
Take the minimum R. Okay. And now you see how to do it, right? If there's a finite number, if you've got a finite number of sets, well, you can take the minimum R, right? But the problem with an infinite number of sets, is that there's not necessarily a minimum R. Okay. You guys getting this? Some people are nodding, some people are not nodding. Close your eyes for a second. on a scale of 1 to 5, how confused are you? 5 is most confused. Okay, put your fingers down. Thank you. There's a wide range. There's a wide range. Okay, so let's run that by again. Okay, so what does open mean? Right, open means every point is interior. Right? Every point is interior. Right? Every point. Right? Every point you can find an interval. I'm sorry. You can find a neighborhood around it contained inside the set. Okay, so now we're trying to show that if E1 and E2, well, let's just do it for two sets. If E1 and E2 are open, so is E1 intersect E2. Right? If you understand this two-set example, then you understand the finite example. Right? It's basically the same thing. Okay, so you say, well, I've got these two sets. And I choose some point, so pick some point x in the intersection. You want an interval, a neighborhood around x that's contained in that set, right? Everybody okay? Anybody confused at this point? Okay. Right? So you say, well, look, this point is contained in E1, so I know that there's some ball around it that's contained in E1, right? This point is also in E2, so I know there's a ball around it that's contained in E2. The smaller of those balls will be contained in both E1 and E2, right? So, let me get it here. Right, so E1, I write it in full generality here. EI open, X is in EI, and EI is open. So there exists an R1, a radius Ri, such that n Ri X is contained in EI. Right? For each I from 1 to n, xi lies in each of those sets, each of which is open, and so there's a radius that works for that point and that set. Right? Then let R be the minimum of R1 to Rn. Right? Then the neighborhood of radius R around X is contained in EI for all I. Right? For all of those I. Right? Because it's the smallest one. Right? And thus, the neighborhood is contained in the intersection of the EI, and so xi is interior to that finite intersection. Is that all right? Yeah, Mike.
Could you explain again, why the smallest, we know that's contained in everything, that taking the small series?
So it's this picture here, right? We're trying to show that, I'll do it for intervals. Okay. So here's this one interval, and here's this other interval. Okay. And we're trying to show that this intersection, which is this thing right here, is still open. It's obviously open, but just pretend it's not clear to you. Okay. So you say, okay, we want to show that this is open. We want to show that this intersection, so let's call this I1 intersection I2, is open. Pick a point x in there. Okay. To be open, we have to be able to find an interval around x that's contained in I1 intersect I2. right? And so what you do is you say, well, look, I know this guy is in I1, right? X is in I1 because it's in I1 intersect I2. And so I know that I can find an interval around it that I1 is open, so I can find a radius R1 that works for I1. Okay. I also know that I2 is open, and I can find a radius that works. I can find an interval around there that works for I2, right? That one has this radius R2. Well, the smaller of those two radii is going to be smaller than the other radii, right? So we let R be the minimum of R1 and R2. Well, that guy is contained, it's certainly contained in I2 because, that's the one that worked for I2, and it's certainly contained in I1 also because the radius here is smaller than the radius here, which was contained in I1, right? So the minimum radius is going to work for all of the sets in that intersection. Yeah.
So why can't we do the same thing for the infinite case?
Yeah. So what happens if we have infinitely many sets, right? Then when I take the minimum of those infinite many sets, what does that even mean? The minimum of an infinite number of radii, right? So suppose the radii are Rn equals 1 over n, or something like that. Well, first off, there is no minimum radius. You can't talk about a minimum for an infinite set, right? So, and even if we did, what would that be? The minimum would be 0. If there weren't a minimum, it would be 0. Okay. Everybody, okay? You feel all right? Okay. Let's go on. Okay. Okay. So the next thing we're going to talk about is closure. Closure and closedness. Okay. You all know what closed means, right? Closed, we have two definitions at this point. Right? Our definition was that, contains all limit points. All of its limit points. Right? But we also saw that was equivalent to saying that E complement was open. Right, that every point in the complement was open. Okay, and we denoted by E prime the set of all limit points. Right, so this is to say that E prime is contained in the set. Right, if the set contains all its limit points, then it's closed. Okay. So, so we introduced the following definition. The closure of E, denoted E with a bar over it, is defined to be E union its limit points. Okay. E and all its limit points thrown in. Okay? So for example, right, like if I say we have the interval 0, 1, right? What's the closure of the interval 0, the open interval 0, 1?
The closed interval.
The closed interval 0, 1? Yes. Right? So the closure, we throw in the limit points, which are the endpoints here. That would close it. That would be the closure. Okay. What's the closure of Q in R? What are the limit points of Q in R? R. Right? It's just R, right? Because all the limit points, everything in Q is already a limit point of itself, but then you also throw in the irrational points. Right? Those are also limit points. So that would be the closure. Okay. So we're going to prove some facts about the closure. So here's the theorem. So first off, the closure is closed. The closure is a closed set. 2, a set is closed if and only if it equals its closure. 3, if you have a set contained in another set, and that bigger set is closed, then the closure of the set inside is contained inside of F. So let's think about this proof of A, right? We want to show that E bar, the closure, right, which is E union E prime, is closed. Okay, in other words, it contains, i.e., it contains all its limit points. Okay. Of course, it already contains all the limit points of E, right? We know that already, right? What we're trying to show is that it contains the limit points of E bar, right? We want to show that it contains the limit points of E bar. That's a different statement, but it turns out to be kind of the same statement. Okay, so you say, right, we want to show if this doesn't make you more confused, we want to show that the limit points of E bar are contained in E bar, right? That's what we're trying to show. Okay. So you say, okay, so take some point x in E bar prime, right? Take some point that is a limit point of E bar. Okay. We want to show that that guy actually is in E bar already. Okay. Right, so I want to show that that guy is in E bar already. Okay, so what does that mean? Like, what does it mean to be? What does it mean to be in E bar prime? Right. Take 10 seconds and write down what this means. Yeah. Or draw a picture of what it means, or something. Put down something that means something to yourself. Okay, so what does this mean? To be in E bar prime means that your limit point of E bar In other words, what does it mean to be a limit point of E bar?
You're a limit point of E as well. That you're also a limit point of E.
Why? That is what we're trying to show in some sense, right? We're trying to show that, right? It's true, but it's not obvious. Yeah. So, but I just love the definition actually. What does it mean to be a limit point of E bar? It means that definition of limit point.
There's some neighborhood that doesn't have elements of E bar. Every neighborhood.
You're right, to be a limit point, being a limit point of E bar means that every neighborhood, something,
Contains some points of E bar?
actually contains infinitely many points of E bar, right? That was something. So remember when this is Hitler's complaint, right? Like all too many definitions, and none of them seem to have none of them seem intuitive. Yeah, but the game at this point is basically to take each of those definitions and then create in your brain some sort of idea of what that means, some sort of translation. Okay, so that's sort of what we're trying to do here. With the examples, you have some examples, right? What's a limit point? Limit point is this guy at the end. What does that mean? It means that no matter what punctured neighborhood you take, there's always some intersection with the set, right? So gradually sort of like hone down that definition. Okay, so we want to show, right? So now we know that. Okay, so take some point that's a limit point of E bar. In other words, for every punctured neighborhood. For every punctured neighborhood and R x star, there are actually infinitely many points of E bar in it. Okay, and we want to show that actually that guy must be. We want to show that forces us to be an E bar itself, right? We want to show that forces us to be an E bar itself. Okay. There's infinitely many points of E bar in every one of your neighborhoods. Here's our guy X. Every one of your neighborhoods, there's infinitely many points in E bar in it. Does that should force us to be an E bar itself, to be a limit point of E, right? To be a limit point of E. Okay. So so you say, okay, right, we want to show that this guy is actually an E bar itself. E bar is, of course, E intersect E union E prime. Okay, so you say, okay, well, take any punctured neighborhood. Take any punctured neighborhood of X, right? We want to show that it intersects E. Right. If we can do that, then we're done, right? X would be in a limit point of if E would be a limit point of E. Okay. So here's X. we take some neighborhood around it. We know that every punctured neighborhood has infinitely many points of E bar in it, right? So either there's some point of E bar in here, either there's some point of E, or there's some point of E prime in here, right? Right. So we know there's either a point of E or a point of E prime in E. Right. If it's a point of E, then we're done, right? If it's a point of E, then we're done, right? If it's a point of E prime, so suppose we get this guy, and let's call it P, and this guy is in E prime. Okay, it's not in E, but it's in E prime. That's still okay, right? Because this guy is itself is a limit point of E. Well, what does that give us? That gives us that every neighborhood of this guy, intersects E. Every punctured neighborhood of this guy intersects E, right? So just take, as we did before, take a radius that's contained inside of this guy, and then you know that there's somebody of E inside there, and so that point of E will be inside the bigger guy. Yeah, Ritika.
I'm a bit confused why, if there is a point of E inside, we're done. Like, I don't understand. I guess I'm just a bit lost and not able to follow.
Okay. Let me start over. I'll sketch it out again. Okay. So, remember what we're trying to do. Half of this is maintaining your sanity. Okay. So, we're trying to show that this set is closed, right? In other words, that it contains all its limit points. Okay. So choose a limit point. Choose X in E bar prime. Okay. We'll show that this X is actually contained in E prime. Okay. And being in E prime means that it's in E bar.
Okay.
Right. So that's the goal, right? Because we're trying to show that this thing is contained in that thing. Okay. So this guy is in E bar prime, right? This X is in E bar prime. We want to show that it's in E prime, right? So take a punctured neighborhood. Take a punctured neighborhood of that point X, right? We're hoping that there'll be some element of E inside there, right? As long as we can guarantee that there's an element of E inside there, that means that we've shown that every punctured neighborhood contains an element of E. In other words, that this guy is a limit point of E. Okay? So you said, okay, take some neighborhood, take any punctured neighborhood around X, right? We know that X is in E bar prime, right? Being an E bar prime means your limit point of this, which means that there must be some element of this union in there, right? Right. So we know. So since X is in E bar prime, we know that there's some point P in that punctured neighborhood. Right? Okay. So here's the point P. If that point is in E already, then we're done. Right? Right? Because that's a good thing, right? So if P is in E, then that's already good. If P is not in E but in E prime, right? Suppose this guy is in E prime. Well, it's still in E prime, and so we can, being in E prime means that every punctured neighborhood of P contains an element of E. So there's some guy in here that's in E. So we found the guy in E, right? Right? This would imply that there exists some element of E such that E is still contained in the punctured neighborhood. In either case, we found an element of E in the punctured neighborhood, and thus X must be in E prime. Okay, clear now?
Yep.
Okay, very good. Okay. I thought maybe this way would be clearer than the way that Rudin does it. Rudin looks at the complement and shows that it's open. That's also okay, but I thought this would be easier. I don't know. Ooh. Okay. Okay, so we've just shown that E bar is closed, right? So remember what we're doing. We wanted to show that E bar is closed. We wanted to show that a set is closed if and only if it equals its closure. And we wanted to show that if E is contained in F and F is closed, then E bar equals F.
Or E bar is a subset of that.
I'm sorry, E bar is a subset of F. Thank you. Thanks. Okay, let's do the second one. Okay, so we want to show that if E is closed already, then E equals E bar. Okay. The backwards proof of B, the backwards direction is straightforward, because you say, well, look, if E equals E bar already, in A we said that E bar is closed, right? Then E bar, since E bar is closed, E is, because they're the same thing. Right. We just proved that E bar is closed. So if E equals E bar, well, you're closed. Okay. Going forwards, if E is closed, then E prime is contained in E. Right? E prime is contained in E, but then that tells us that E bar, which is E prime union E, is contained in E. So what we're doing here, we're trying to show that these guys are equal to each other. We're trying to show that these two sets are equal to each other, and so we'll do that in two parts, this part and this part. Okay, we'll show containment in both directions. Okay. E is certainly contained in E bar, right? E bar is, E union E prime. Right. So now the backwards direction, that part's easy. The backwards direction showing that E prime is contained in E, well, if you're closed, then E prime is contained in E, and so E bar, which is the union of E prime and E, is going to be contained in E. Okay. Yeah, Harrison.
Couldn't you just say that since E prime is a subset of E, by the definition of that it's closed, right? Then you can argue that E union E prime is equal to E, and thus E equals E bar.
Say that one more time.
E prime is a subset of E because E is closed.
Yep.
Then that means the union of a set and its subset is E.
This is E,
Yeah, and E bar.
which is E bar.
Yeah.
Yeah, sure, same thing. That's even better. That's even better, yes. Thanks. Yeah, rather than going in both directions. That'll certainly work. Okay. Okay. And then the last one, right, so we have E contained in F, and F is closed. You want to show that E bar is contained in F. Okay. The proof is, right, we want to show that E union E prime is contained in F. Okay. But F is closed, right? F is closed, so F is the same thing as F bar, right? Which is, by definition, F union F prime. Okay, and certainly, E is contained in F, and E prime is contained in F prime. Right. So the above is true. Right. We're trying to show this, right? That E union E prime is contained in F, but F is F union F prime. Right? E is contained in F, and E prime is contained in F prime. Take 30 seconds and convince yourself that E prime is contained in F prime. Right? What does it mean to be an E prime? It means you're a limit point of E, right? Right? Is every limit point of E a limit point of F? Every point of E is a point of F. Right? Every point of E is a point of F. So if you're a limit point of E, you're definitely a limit point of F. Right? If you can be approximated by points in E, well, those points are in F. Right? So you're approximable by points in F. Okay. So that's true. Yes, Rishi.
The more general statement that we've just shown is just that the closure is like monotone, right? So like if E is a subset of F, then the closure of E is a subset of the closure of F.
Yes.
And then this case just falls out because closed sets are their closure.
That's true. Yeah. Yeah, that'll do. Okay, how are you guys doing? I feel a slight cloud of despair. Is everybody okay? Are you guys okay? Don't worry. Okay, don't worry. This is sort of like the technical. There are parts where we sort of have to chase down definitions. Okay, so we chase down the definitions. We establish certain properties. Then we sort of ignore the. Then we just sort of remember the properties. Okay, but yeah, you do have to understand these things, but don't be in despair if it's not completely lucid. Okay, that's fine. Okay. Yeah. Okay. I'm gonna. So there's actually a couple more technical results that I should prove at this point, but I'm gonna put them off. Okay, just because I don't want the cloud of despair to thicken. Okay, so instead of descending further into technicalities, which we sort of would establish and then ignore almost immediately, I'm going to jump a little bit and go to this crucial definition of compact sets. Okay, this may not make you any happier. Okay, in fact, I kind of doubt it. But anyway, this is what we're going to do. Okay, so definition. So you have a set that's contained in X, where X is a metric space. Okay, so let's, the trouble with the definition of compactness is that it's kind of, one has to define sort of a string of definitions first, and then get to the definition of compactness. Okay, so let's start off with this first definition. So any collection of open sets G alpha that are in X, of course, such that the union of the G alpha covers E is called an open cover. Open cover of E. Okay, so let me kind of give you a dull example. Like if my set is the entire, if E is all of R, okay, and I let G n denote the interval negative n, right, then the union of the Gn, as n goes from 1 to infinity, will cover the entirety of the real line, right? That'll cover the whole real line, right? And so that's an open cover of R. Okay. Okay. So it's just open sets that cover your set. Okay. Okay. So here's the definition of compactness. So you have some K set sitting inside of X. If K has the property that every open cover contains a finite subcollection. Every open cover of K contains a finite subcollection that is still an open cover of K. Then we say K is compact. Okay, then we say K is compact. Right, so no matter what open subcover is given, no matter what open cover is given, there exists a finite subcover. Is how people usually abbreviate it. Okay, what it means is that whatever open cover you're given, there's always some finite subcollection of that cover that still that will still cover your set. Okay. So I'll begin with the stupidest of examples. Okay. So like your set consists of a single point. Okay. Okay, that is a compact set. Okay, that's a compact set, right? Because no matter what cover you have, so suppose somebody gives you a cover. Suppose you're given a cover, right? In other words, like the union of the G alpha contains your set. Okay. Well, one of those guys had better cover that point, right? Otherwise, it doesn't cover, right? You know, so you know there exists some G alpha naught that contains that point, right? So this is your finite subcover. Right. So what we've just shown is that no matter what covers somebody gives you, there's definitely going to be a finite subcover, right? And so this set is compact. Okay. Let me give you an example of a non-compact set. R. Okay. R, the real line. And to show that something's not compact means that you can find a cover that doesn't have a finite subcover, right? All you need to do is to find one bad cover, right? Right? To show that something's compact means that whatever cover you're given, you can find a finite subcover, right? For that to fail means that there's some cover that doesn't work, right? So to show this guy is non-compact, we have to find a bad cover for it, right? A cover for which no finite subcollection will cover the whole thing. Okay. So you could do something like say let G sub n equal n comma infinity, right? As n ranges over the integers. Right. That's a cover, right? The union of the G sub n certainly contains R, right? So is a cover, right? But no finite subcollection is going to work, right? No finite subcollection is going to work because if I take a finite subcollection, well then there's going to be some smallest index, right? And we're not going to have anything to the left of that smallest index. We're going to miss all that stuff on the left, right? So no finite subcollection works. This is a bad cover, right? So we found a cover for which there is no finite subcover, so this set is not compact. Right? Okay. So what does compactness mean? It means that your set is kind of finite. Okay, it's like a finiteness for infinite sets. Okay, let me give you a couple of more examples that will kind of illustrate that point. So consider the set. The set of numbers 1 over n from n equals 1 to infinity. Okay. So 1, 1/2, so here's 0, 1, 1/2, 1/3, 1/4, and so on and so forth. Okay. So this set is not compact. This set is not compact. Okay. And the reason is that you can find a bad cover for it. You could, for example, take intervals 1 over n, comma 2, say, as n goes from 1 to infinity. Right? So that would be, 1 comma 2, 1/2 comma 2, 1/3 comma 2, 1/4 comma 2, and so on and so forth. Right? And you see that the union of all these guys, right? The union of all these guys, all these guys certainly covers my set. Certainly covers my set, but I can't take any finite subcollection of them, right? If I take a finite subcollection, well, that means it's going to stop at some point, right? I'm going to miss all these guys that are close to the origin, okay? Right? Now consider that set, but also throw in the origin. Okay. Consider that set and throw in the origin. Okay. That set is compact. That set is compact. I'll kind of sketch out, let me kind of sketch out why. So here's 0, 1, 1/2, 1/3, 1/4, and so on and so forth. Okay. So the reason is that if I have somebody gives me an arbitrary open cover, well, that open cover must cover 0, right? Right? It's an open cover of my set, so it's got to cover 0. 0 is in my set, right? So there must be some set that covers 0. When it does that, it covers all these infinitely many points, and then there's only finitely many other points, right? Right? And so, and then for the finitely remaining other points, you say, well, I've only got finitely many other points. This must be contained in some set. This guy must be contained in some set. So there's finitely many other sets, and then there's this one guy that takes care of everything else. Okay. So that's why this set is compact. Actually, I think this might be a homework problem. Why did I show this? It's too late. Okay. Okay. So I hope you're starting to see the compactness of the set, forces the sort of finiteness of it, right? It forces no matter you've got an infinite cover of it, but you can always find a finite subcover, right? There's always some finite set of neighborhoods that will cover your whole set. Your set can always be no matter how complicated your initial cover, there's always something very simple. There's simpler structure underneath. Okay. So, yeah, finiteness for infinite sets is how you want to think about it. Okay. Okay. Let's do a couple of properties, and then I'll fix. I need to fix some of the details later, but I'll just do some properties here. Okay, yeah. Okay, so 1, compact implies closed. Okay, so here's the picture. Here's your compact set. Here's your ambient space, the metric space. You want to show that K is closed. Okay, so what we're going to do is we'll show equivalently that K complement is open. Okay. So pick a point x in K complement. We want to show, of course, that there exists some neighborhood around it that's contained in K complement. Right? We want to show this point is interior. In other words, that there's a neighborhood around it that's contained in the set. Okay. So we're trying to find some neighborhood here that's contained, that doesn't intersect K. Okay. That doesn't intersect K. Okay. So what we do is we say, well, let's take every single point of K. Okay. Take a point of K and take the distance to our point x. Okay. So let's call this guy little k. Right? Take the distance to x and take a neighborhood of half the distance. Okay. Right? Then, and do that for every single point, right? For every single point, we're going to take half the distance. Every single point, we're going to take a neighborhood of whose radius is half the distance to that point. And so each of those guys doesn't intersect, right? Each of those guys doesn't intersect x, right? On the other side of things, if we look at it from x's perspective, right? Here's k. We've taken half the radius, right? So when we take that half radius, right? These neighborhoods are disjoint, right? These neighborhoods. So for each point in K, we create a neighborhood and we create a corresponding neighborhood and these two neighborhoods are disjoint from each other. Okay. Now, if there were only finite points of K, what would we do? Suppose there's only finitely points, K1, K2, and K3. Okay. Well, for each of these guys, we could create a neighborhood, right? A neighborhood that doesn't intersect the neighborhood centered on x, right? We'd have K2, same thing. We've got this guy, half the distance. This guy's neighborhood doesn't intersect this guy's neighborhood, right? Right? And then what you do is, I hope clear, you would intersect these guys, and that would give you a neighborhood around x that doesn't intersect K, right? Because we stayed away from it, right? We stayed away from, there was only 3 points in K, right? And this thing stays away from the neighborhoods around those 3 points, each of the neighborhoods around those 3 points. Okay, but K is infinite, but K is compact. Right, so it's basically finite, right? So you say, well, look, for each K and K, cover it with an distance from K to X over 2 centered at K. Okay. Okay. Then, that neighborhood, distance of K to X over 2 around K, intersect distance from K to X over 2 around X is empty, right? The two corresponding balls don't intersect each other, right? K is compact, so we can cover K with finitely many of those guys, with some collection n delta k k1x over 2 centered at k1 ... n delta k nx over 2 at k2. Right? So there's finitely many, since this guy's compact, there's finitely many k's that will still cover this whole set. Right? then the intersection of the, well, let me write it this way, then n sub the minimum radius delta k1 u delta kn around x does not intersect that finite cover and thus not k either. Right? Because that finite cover covers k. So we don't intersect that cover, we don't intersect k. Which means that we found the ball, right? So this is the ball. This shows x is interior to k complement, which is what we wanted to do. Okay. We wanted to show that k complement was open, and we've shown that every point is interior. Okay, that's it for today. Goodbye.
Also, I thought on Wednesday, I just had an honor board meeting today that I forgot about.
So you're not going to be on Wednesdays, what you're saying?
No, I'll be at All Stars on Wednesday.